Hello, my wonderful students. You are welcome to another lesson. In our previous class, we rounded off electrochemical cell. But in today's class, we are going to deal on one of the major topics in chemistry, an interesting one that seems to be everywhere, that seems to be very important in every chemical reaction. And that topic is water. We are going to be looking at the structure of water, the shape of water, the physical and chemical properties, its preparation, and the uses. We're also going to do more on its solubility. I mean, the solubility of water as regards to different samples and its application. We're also going to talk about the colloids and we're also going to talk about even the sources of water and the types of water. We will be discussing about soft and hard water. What causes this hardness of water, its advantages and disadvantages, and how it can be removed. So do well, sit back, materials, and watch the videos where thorough explanation are being given.
The chemistry of water. Water is an inorganic molecule that is the most important compound in the body. In fact, a normal adult's body weight is made up of 50% or more of water. A molecule of water has one oxygen atom covalently bonded to two hydrogen atoms. Covalent bonds being the chemical bonds that are formed by the sharing of one or more pairs of electrons by the outer energy levels or shells of two atoms. Water molecules are also polar molecules. Even though the oxygen atom shares electrons with the hydrogen atoms, the electrons are not shared equally within the molecule. This gives the oxygen side of the molecule two partial negative charges, and each of the hydrogens a slightly positive charge. This means that each water molecule can form up to 4 hydrogen bonds with adjacent water molecules. Hydrogen bonds are the result of an unequal charge distribution on a molecule. These molecules are said to be polar. This property allows water to act as a very effective solvent, which means it is able to dissolve or break apart many other substances. Substances that do dissolve or break apart in water are called hydrophilic, which means water-loving. Nonpolar substances that do not dissolve in water are called hydrophobic or water-fearing.
So when drawing the structure of water, you want 1 oxygen and 2 hydrogens, and don't forget the lone pairs of electrons, these 2 lines I'm about to put here. So the hydrogens have a small positive charge, delta positive, and the oxygen a small negative charge, delta negative. The bond between the oxygen and the hydrogen is referred to as a polar covalent bond. Now when you put 2 water molecules next to each other, and each one obviously has the same kind of polarities, delta positive and delta negative, you find the delta positive on the hydrogen attracted to the delta negative on the oxygen of the other water molecule. This forms a hydrogen bond. The formation of this hydrogen bond results in cohesive forces between the 2 water molecules.
We'll learn about natural sources of water and man-made sources of water. Natural sources of water are those which can be found on Earth naturally. These sources cannot be constructed by the human. Man-made sources of water are artificial sources which can be constructed by the human. Natural sources: rain, rivers, lakes, streams, ponds, sea. Now let's see the man-made sources of water. Reservoirs, well, tube well, hand pump, tap, canal, and tanks.
If you wash with soap using rainwater, washing is easy and there are plenty of bubbles. We say the water is soft. But if you use well or tap water, it's sometimes difficult to get a lather and a scum forms. In this case, we say the water is hard. Hardness is usually caused by the presence of calcium ions dissolved in the water. Water coming from rivers or wells has had to flow through the surrounding rocks, and if they contain soluble calcium salts, the water will become hard. So here's a question. Why do you think rainwater is always soft? Pause the video until you have thought of an answer. Well, all the salts which dissolve out of the rocks end up in the seas, but when water evaporates, later forming the rain, the salts are left behind in the seas, meaning that the rainwater is always free of salts and therefore soft. However, gases from the air can dissolve in rainwater, and one of these is dissolved carbon dioxide. When rainwater falls on limestone, that's calcium carbonate, the limestone dissolves slowly, which is how the great caves full of stalactites are formed. Here's the equation. Calcium carbonate reacts with the carbon dioxide in the rain to form soluble calcium hydrogen carbonate. This form of hardness is called temporary hardness because boiling reverses the reaction and the hardness is removed. But the limestone will deposit in your pipes, on the cooking utensils, or in your kettle, forming something we call limescale. And this is also how stalactites are formed in those big caves. Another form of hardness is called permanent hardness, which comes from rocks containing gypsum, which is calcium sulfate. In this case, you do not get limescale, but you still, of course, get a scum with soap. So what is this scum? Well, soap is made by boiling natural fats and oils with sodium hydroxide. The soap molecules, for example sodium stearate, have a long tail which is attracted to oil or dirt, and the sodium ion end which is attracted to water. In this way, dirt is lifted off your hand and the clothes and is carried away by the water. However, calcium stearate is insoluble, so if the water contains calcium ions, the soap will not work until all the calcium ions have been precipitated out as scum. Detergents are sodium salts of compounds called alkyl benzene sulfonates, whose calcium salts are soluble, so there is no problem of scum with detergents. So to summarize, we saw that water becomes hard by flowing through rocks containing calcium salts, and these react with soap to form a scum of calcium stearate, making it difficult to use the soap. Temporary hard water forms deposits of limescale when heated, but rainwater is soft, lathers easily with soap since it's free of dissolved salts.
Water. It's all around us. Makes up 70% of the Earth's surface and about 60% of your body. Let's start with the basics. Water is a colourless and transparent substance. When it is pure, it has no smell and no taste. If you've ever thought that one type of tap water tastes different to another, you're not wrong. Tap water in different areas may have slight impurities from various metal ions. Water is a liquid at room temperature. It freezes at 0 degrees and boils at 100 degrees at standard pressure. But have you ever wondered why the boiling point of water is higher than, for example, methanol? Well, you might know from this video that water is a polar molecule with slightly positively charged hydrogens and slightly negative oxygens. Imagine a bunch of water molecules in a beaker. They are in liquid form, so can move around each other, but the delta positive hydrogens from one molecule are weakly attracted to the delta negative oxygen of another. This is a type of intermolecular force, and it has a special name, hydrogen bonding. Because of this, the water molecules need quite a bit of energy to overcome the hydrogen bonds and escape from the beaker as a gas. Water is a very good polar solvent, so good it's often called the universal solvent. That's a bit of an exaggeration, but it's certainly true that many common chemical compounds will dissolve in water. Here's just a few: hydrochloric acid and many other acids, sodium hydroxide along with other bases, soluble salts such as table salt, sodium chloride, and sugars. Here's a challenge though. Can you think of a large and important type of compound that won't dissolve in water and instead floats on its surface? More importantly, can you think why they do this? Pause the video, think carefully, and resume when you've got the answer. Well, the answer is lipids, or in plain English, oils or fats. They don't dissolve in water because they're non-polar and therefore hydrophobic, meaning they don't like mixing with water. One of the most unusual qualities of water is that it can act as either an acid or a base. A water molecule can either accept a proton and become a hydronium ion with a +1 charge, or donate a proton and become a hydroxide ion with a -1 charge. This is one of the reasons why water is so useful in all sorts of organic chemistry reactions. We already use water for bathing, laundry, many industrial processes, and of course drinking. But perhaps even bigger things lie ahead. You see, many scientists all over the world are working on developing hydrogen as an alternative fuel source. We know it works for this purpose, but there are problems with storage, transportation, and refueling that are holding us back. Nonetheless, a lot of people believe that in the not too distant future, many of our machines and industries will be powered not by hydrocarbons, but hydrogen gas. And where are we going to find an almost limitless potential source of hydrogen to use for these purposes? You guessed it, the humble water molecule.
Colloidal solution, types of colloidal solution and examples of colloids. That what is colloidal solution or colloids? Well, when the size of particles is between 1 up to 100 nanometer and a heterogeneous mixture, we call it colloidal solution or just colloid. For example, consider milk. Milk is a colloid or colloidal solution. Here, a lot of students are confused. Let me clear this confusion. The milk appears to be homogeneous mixture, but its microscopic description reveals that its particle size is between 1 up to 100 nanometer. So this particle size make it not only heterogeneous mixture, but also colloid or colloidal solution. Thus noted down that colloids appear to be homogeneous, but it may not be the case. Also remember that every colloid contains two phases, dispersed phase and dispersed medium. Personally, I call dispersed phase as a solute and I call dispersed medium as a solvent. Dispersed phase is the component that is present in smaller proportion in the colloid, while dispersed medium is the component that is present in larger proportion in the colloid. For example, milk is a colloid. It is made from liquid fat and water. So liquid fat being present in smaller proportion is the dispersed phase, while water being present in larger proportion is the dispersed medium. Here is a bonus MCQs for you. The combination of two gases never forms solution, mixture and colloid. Well, the answer is colloid. For example, consider air. We know that air is a homogeneous mixture of different gases like nitrogen and oxygen. So combination of gases never forms heterogeneous mixtures and never forms colloids. Finally, let me teach you the 8 types of colloids and examples of colloids. The first is gas in gas. We know that gas in gas combination or mixture doesn't form colloid. The second is gas in liquid. The third is gas in solid. Here in this category, gases are present in dispersed phase or in smaller proportion, while liquid and solid are present in dispersed medium or in larger proportion. The name of gas in liquid colloid is foam and its example is whipped cream. The name of gas in solid colloid is solid foam and its example is bread. Now the fourth is liquid and gas, the fifth is liquid and liquid, and the sixth is liquid and solid. Here, in this category, liquids are present in dispersed phase are in smaller proportion, while gas, liquid and solid are present in dispersed medium are in larger proportion. The name of liquid and gas colloid is aerosol, and its example is fog or cloud. The name of liquid and liquid colloid is emulsion, and its example is milk. The name of liquid and solid colloid is gel, and its example is jelly or butter. The seventh is solid and gas. The eighth is solid and liquid, and the ninth is solid and solid. Here, solids are present in dispersed phase are in smaller proportion, while gas, liquid and solid are present in dispersed medium are in larger proportion. The name of solid and gas colloid is aerosol, and its example is smoke or dust. The name of solid and liquid colloid is soles, and its example is pants. The name of solid and solid colloid is solid sole, and its example is alloy. Remember that we do not have a colloid in gas and gas mixture, so we therefore have 8 types of colloids or colloidal solution. What is solubility, effect of temperature on solubility, and effect of pressure on solubility? Now, what is solubility? Well, the amount of solute in grams dissolved in 100 grams of the solvent to prepare a saturated solution at a given temperature is known as a solubility. For example, consider 100 grams water in this beaker at 30 degrees centigrade or at room temperature. Firstly, I add 10 grams sugar and 100 grams water. It easily dissolves in the water. Secondly, I again add 10 grams sugar and 100 grams water. But this time, some sugar dissolved in the water and some sugar settled down at the bottom. This means we have prepared a saturated solution of sugar and water at 30 degrees centigrade. Now listen carefully. I dissolved 20 grams sugar and 100 grams water such that I got saturated solution. Saturated solution means that 100 grams water can only dissolve 20 grams sugar at 30 degrees centigrade. The extra sugar would settle down at the bottom. Thus we say that the solubility of sugar is 20 grams and 100 grams water at 30 degrees centigrade. Let me repeat it. The solubility of sugar is 20 grams and 100 grams water at 30 degrees centigrade. Now, how can we calculate the solubility of a solution? Well, the formula of solubility is equal to mass of the solute over mass of the solvent and 200. Here, the mass of the solute or sugar is 20 grams that are dissolved in 100 grams solvent or water. Hence, we write solubility is equal to 20 grams over 100 grams and 200. Thus, we get solubility is equal to 20%. It means that the solubility of sugar is 20% and 100 grams water at 30 degrees centigrade. Here, if we increase the temperature of water, solubility of sugar will be increased. Thus, remember that solubility means how many grams of solute is dissolved in 100 grams of solvent at a particular temperature. Finally, let me teach you that solubility depends upon 3 factors: nature of solute and solvent, pressure and temperature. For instance, the solubility of salt and water at 30 degrees centigrade would be higher than the solubility of sugar. It is because when the molecules of solute are similar in structure and properties to the molecules of solvent, solubility is usually high. Secondly, if the solute and solvent are gases, solubility is affected by the pressure. For instance, in carbonated drinks, carbon dioxide is dissolved in water at high pressure. Once you open the bottle, pressure decreases and carbon dioxide gas evaporates. As a result, solubility decreases. To learn the effect of temperature on solubility, you must learn 3 chemical reactions: exothermic reaction, endothermic reaction, and isothermic reaction. For example, when you add calcium hydroxide to the water, heat is released in the surrounding. This is known as an exothermic reaction. Here, if we increase the temperature, solubility of calcium hydroxide in the water decreases. Secondly, when you add ammonium chloride to the water, heat is absorbed from the surrounding. So it is endothermic reaction. Here, if we increase the temperature, solubility of ammonium chloride and water increases. Thirdly, when you add salt to the water, heat is neither absorbed nor released. So it is isothermic reaction. If we increase or decrease the temperature, the solubility of sodium chloride or salt doesn't change in the water. Thus remember that increasing temperature in exothermic reactions decreases the solubility. Increasing temperature in endothermic reactions increases the solubility, while increasing or decreasing temperature in isothermic reactions doesn't affect the solubility. This was all about solubility, effect of temperature and pressure on solubility.
In this lesson, there are two main tests for the presence of water. Note that these tests do not confirm the purity of water, only its presence. The first test involves the usage of anhydrous copper 2 sulfate, which is an off-white solid. The term anhydrous means without water. In the presence of water, anhydrous copper 2 sulfate becomes hydrated copper 2 sulfate, which is bright blue. The term hydrated means with water. Another method to test for water is by using cobalt 2 chloride paper, which turns from light blue to pink in the presence of water. The same concept seen in the copper 2 sulfate test applies to the cobalt 2 chloride test. The anhydrous form of cobalt 2 chloride is light blue, whereas the hydrated form is pink.